day, everybody, and once again we're back together. And today I just thought that I would just discuss this short question from the Eastern Cape exam. Right, it's last year's prelims, so please, if you haven't subscribed, do the right thing. Let's get right into the question. So it is based on chemical equilibrium. They say that sulfur trioxide gas is injected into an empty container, which is then sealed. The following reaction takes place inside the container rather. Okay, so we are given there that reaction and we can see as it takes place, right? Now they say to us the graph below shows the changes in the reaction rate against time for the first 20 seconds. Right, so they ask us to write down the meaning of the double arrow in the equation. So please remember that whenever we see these double arrows, they simply indicate that it is a reversible reaction. Okay, please remember that it means that the reaction is reversible, right? And in this case, it means that products can be converted back into reactants. Okay, right, now they say what is represented by the horizontal section of the graph between t equal to 10 minutes and t is equals to 15 minutes. So remember, any time that we've got a reaction rate graph, or even when it comes to chemical equilibrium graphs, right? So what does the horizontal section represent? It represents chemical equilibrium, okay, or you can say dynamic equilibrium, right? So in this case, as long as you've indicated that this is actually in relation to equilibrium. Right, now ladies and gents, I want you to note as we are reading this graph, remember, so you've got two reactions here. You've got the forward and the reverse reaction, right? Now, how do I know rather which one is which, right? Now remember, at the beginning, I only have reactants, and so there are no products that are formed, so you can't have the reverse reaction, right? So right at the beginning, the rate of the reverse reaction would be 0, right? So which means that our dotted line is actually showing us the rate of the reverse reaction. Okay, so that would mean that our solid line would be the forward reaction. So please note that. So this would be our forward reaction and this would be our reverse reaction. Please note, this does not indicate the amounts that we have, right? But this is the graph on the rate of reaction. Okay, so now let's go to the next question. So they say t is equals to 15 minutes, right, of the reaction mixture in the container was changed, right? Rather, they say the temperature of the reaction mixture in the container was changed. So I want us to note in this case, what happened at t is equals to 15? So now you'll notice that the rate of the forward reaction simply surged up, right? So this actually indicates to you that the forward reaction is actually the one that depends on temperature the most. Remember, as I increase the rate of the, as I increase temperature, right, we usually favor the endothermic reaction. So automatically that tells us that the forward reaction must therefore be favored. Why? Because we see that the forward reaction is the one that was favored the most. It's the one that actually increased the most. And it does also indicate to us that that was an increase in temperature. Now, let's answer the questions that are asked. They say, was the container cooled or heated? It will definitely be heated, right? And in this case, they say to us, and by the way, why am I saying heated? Because the rate of the reaction, both reactions increased. However, we noticed that the rate of the forward reaction was the one that was that increased the most. Now they asked us, is the forward reaction exothermic or endothermic? I would definitely say the forward reaction is endothermic. Right, now they say explain your answer to question 6.1.4 by referring to Le Chatelier's principle. Right, now first of all, remember I will actually state an increase in temperature. Okay, an increase in temperature will favor the endothermic reaction, right? Favors. Okay, let's try and favors the endothermic reaction, right? So in this case, the forward reaction is favored. Okay, right. So the forward reaction, okay, is favored, or you can say that the forward reaction increases, or the rate of the forward reaction increases the most, right? The forward reaction is favored, okay, right? We can say the rate increases, okay, increases the most, right? And so that means that the forward reaction must be endothermic. Okay, so we're going to say the forward reaction is endothermic, right? Endothermic. Apologies about this terrible handwriting. Okay, right. My handwriting has mood swings sometimes. Right, so that is really how we're going to explain it, ladies and gents. All right, let's go to the next portion. So they say to us, at 20 minutes, the pressure inside the reaction container is increased, right? They say by decreasing the volume at constant temperature. Now, quickly, I want us to go back to the reaction, right? So, in this case, remember that when I increase pressure, right, I am going to squeeze, right, or I'm going to make the space much, much smaller. So what usually happens, ladies and gents, is that I will then favor the side with the least amount of gas amounts, right? So now, if you notice here, I've got 2 moles of gas on the left-hand side. I've got 3 moles, so that's the 2 plus the 1. So I've got 3 moles of gas on the right-hand side, right? So now, what will happen? If I increase the pressure, making the space smaller, I will actually favor the reverse reaction, right? So, yes, both reactions rates are going to change, are going to increase, but the one that will surge the most will actually be the reverse reaction. And the reason for that is that we've got a smaller amount of gas on the left-hand side, on the reactant side. So what's going to happen? So they say to us, redraw the graph below and indicate the effect that an increase in pressure will have on the reaction rate up until a new equilibrium is established. Now, what we will see, all right, I know my graph will not really be the best, but the dotted line will be the one that surges up the most, right? And thereafter, right, what should happen is that, of course, it will surge up initially, but eventually we get to a point where we are going to reach another equilibrium. But remember, we're not only going to increase the rate of the reverse reaction, but it means the rate of the forward would also increase. However, it will increase more gradually than the reverse reaction. So this is what you're going to find as you change the pressure, right? Okay, so let's go to the next portion. They say to us, carbon and carbon dioxide are mixed in an empty 2 cubic decimeter container, which is then sealed. Okay, so we are looking at another reaction. This has got nothing to do with the previous question. Right, now they say to us, the following balanced equation represents the reaction that reaches equilibrium, right, in the container at 700 degrees Celsius. Right, so there's our reaction, and we can see there we've got carbon, which is a solid. And remember, please, you do not include it in the equilibrium constant expression. Right, now they say to us, at equilibrium, it is found that the concentration of carbon dioxide is 0.05 and 0.4 moles of carbon are present, right? They say the equilibrium constant for this reaction at 700 degrees is 0.05. All right, now they want us to calculate the percentage of carbon that has reacted. All right, ladies and gents, let's take it one step at a time, right? So we're going to start with our rise table, ice table, whatever you might want to call it. Okay, so let's talk about what it is going to look like. Okay, so of course I'm going to include all my reactants and products. And please note, when you draw the table, you do not include gases only on the table, you include everything, right? It is only in your equilibrium expression where we are going to exclude solids and liquids, right? So we've got carbon. We'll have carbon dioxide. Remember, in this case, these are my reactants. And we've got 2CO. In this case, that is going to be my product. Okay. Right. Now, ladies and gents, notice that the ratios, you've got 1 here, right? 1 carbon. And you've got 1 mole as well of, or rather the coefficient or the ratio is 1 for carbon dioxide, and it is 2 for carbon monoxide. So we've got initial, right? That's in moles. We've got change. That's also in moles, right? We've got equilibrium, right? That's also in moles. And we've got our equilibrium concentration, and that's going to be in moles per cubic decimeters. Now, ladies and gents, let's start with what we have, right? So they didn't give us much information, right, at the beginning, right? They just told us that we've got carbon and carbon dioxide that are mixed into an empty empty container. So what it means is that our product is actually 0 at the beginning, right? Remember, our product is carbon monoxide. And then they give us the picture of what happens at equilibrium. They say that it is found that the concentration of carbon dioxide, right, is 0.05. So now, at equilibrium, remember they spoke about concentration, not the number of moles. So that is going to be 0.05 over there, right? And then they told us that 0.4 moles of carbon are present. So with carbon, they give us the moles. So we've got 0.4 moles that are present there. Right, now, ladies and gents, they also gave us the equilibrium constant of this reaction, right, at 700 degrees. They say it is 0.05. So now, remember, which ones are gases? It is carbon dioxide, which we have the value of. We don't have the equilibrium concentration of carbon monoxide. Now, remember that for carbon, we cannot actually have the concentration. Remember that the concentration of solids and liquids are constant, right? So as a result, we do not include it in the equilibrium in the equilibrium expression, Kc expression, right? So now I can actually find out what is the amount of carbon monoxide at equilibrium. So I can say, well, my Kc value, that's going to be the molar concentration of my products, which is CO, right? It is a gas. So this is squared. Remember that the coefficient becomes the power in this case, or the exponent, right? So in this case, divided by the molar concentration of carbon dioxide. Remember, in this case, the coefficient is 1. So as a result, we will not put any exponent there, but we know that the exponent is 1, right? And we know this is equal to 0.05. 0.05, right? That is our Kc value, right? That is given to us there. Okay, so what I'm going to do is just substitute what we have, right? So this is 0.05 squared over carbon dioxide. Okay, actually, I'm looking for carbon monoxide. Apologies about that. Okay, so this is going to be carbon monoxide rather. Okay, squared divided by the amount of carbon dioxide at equilibrium, right? It is carbon dioxide, that is 0.05. So this is going to be 0.05. And this is going to be equal to the Kc value, which is 0.05. I'm sure you can see where this is going because carbon dioxide squared, okay, carbon monoxide rather squared, right? Or the concentration of carbon monoxide squared is equal to 0.05 squared as well, right? So if I take the square root on either side, I'm left with the concentration of carbon monoxide being equal to 0.05. Okay, this is in moles per cubic decimeters. Now I can include that back, right? So I can say, well, it means this would be 0.05. Now we're going to work our way backwards, right? And say, well, can I find the number of moles of carbon monoxide at equilibrium? Yes, I can, because my volume is given as 2. So I know that concentration is number of moles divided by volume, but now I'm looking for the number of moles, right? So in this case, number of moles would be concentration times volume, right? This is for carbon monoxide. So concentration is 0.05. My volume is 2, and that will give me 0.1 moles. Okay, so I'm going to put that there. So this gives me 0.1. But the same is true for carbon dioxide as well. Notice that in this case, if I calculate, it will give me exactly the same calculation. I've got 0.05 at the end, right? Multiplied by 2, which is the volume. And so that will give me 0.1. Right, so remember, I am trying to work my way into finding out. They said to me, I must find out the percentage of carbon that reacted. So I can't find the one that reacted if I don't find, in this case, the initial amount, right? So now, which means, where do I have the most information? Well, with carbon monoxide, I know I started with nothing. And at the end, I've got 0.1. Well, how much did I produce in that case? Well, it means that I must have produced 0.1, isn't it? So this means that the amount of carbon monoxide that we were able to produce is 0.1 moles. All right, ladies and gents, notice now we're going to use our stoichiometric ratios, right? For every one of this, there's 2 of those, right? So let's do that. So for every 1 carbon dioxide, I get 2 carbon monoxide, right? So for how much carbon dioxide, or how much carbon dioxide will I have in order to produce 0.1? Notice I start with the ratios. 1 is to 2. So how many is to 0.1, right? So 1 is to 2. How many is to 0.1? And all you do is cross multiply, ladies and gents. So this gives me 2x is equal to, so 2 times x will give me 2x. 1 multiplied by 0.1, that's 0.1. And divide both sides by 2. And so that will give me 0.05. Okay, it looks like a very popular number in this question. So I know this will be 0.05. But notice, ladies and gents, again, I'll do exactly the same calculation for carbon, right? In this case, it means for every 2, again, there is 1 carbon, right? So for every 0.1, there will be 0.05. It will be exactly the same calculation as carbon dioxide. Now, remember, what am I looking for? I'm looking for the one that I started with. Okay, so how much did I start with so that I use 0.05 and end up with 0.4, right? Now notice in this case, I'm taking it backwards, right? All right, so which means 0.4 plus 0.05 will give me 0.45. Okay, now think about it. If I started with 0.05, I use 0.05, of course at the end I'm going to have 0.4. Well, the same is true for carbon dioxide because it was a reactant, right? In this case, it means that 0.1 plus 0.05, I will have 0.15 at the beginning, right? If I started with 0.15 and I use 0.05, well, guess what? At the end, I'm going to have 0.1. Well, reversing this would be actually the opposite. If I have 0.1 at the end, right, in this case, I must have produced 0.1, right? So 0.1 minus 0.1 will give me 0. Remember, that is a reactant and I am reversing the process. I hope that makes sense, guys. Okay, so now let's answer the question. They said calculate the percentage of carbon that reacted. Now, to get the percentage, which one reacted? It is the one that changed. That's where the reaction took place, right? So I'm going to take the one that reacted divided by the total amount of carbon that we started with. So percentage that reacted, percentage carbon that reacted, okay, will be the number of moles of carbon. So this will be 0.05 divided by the total amount of carbon that we had at the beginning, and this is multiplied by 100. So let's do that quickly. So we've got 0.05 divided by 0.45, right? And this is multiplied by 100. And what do we get there? We get 11.11%, right? And that is how we are going to get the amount of carbon, or rather the percentage of carbon that reacted. Ladies and gents, this is where we are going to conclude the question. I really hope that you are able to understand this. And as you prepare for the exams, I am going to be giving you even more and more of these type of questions where you are going to be able to do, just practice a bit as you will be writing prelims. Otherwise, from me for now, I'll see you guys next time. Shap, shap.